Hi everyone, my name is Chen Yuan from University at Buffalo. Today, I'm gonna introduce our optimized building blocks for secure multi-party computation. This work is joint with Marina Blanton from University at Buffalo and Ahreum from Songzhenyan University. Secure multi-party computation enables a set of parties to interact and compute a joint function of their private inputs while revealing nothing but the output. So lots of common options we use every day almost for free becomes non-trivial in the environment of SSC. For example, this is a piece of pseudocode for binary search. If we want to implement this in the environment of secure multi-party computation, there are lots of things we need to track. First thing is that all input data, no matter the array or the target value, all this data may contain sensitive information that its owner may not want to reveal it to other parties. So we need to protect the data. But only protecting the data is not good enough. Sometimes, even the memory access pattern could also reveal information about the private input. Depending on a different condition, you can have a different memory access. But if someone could observe this memory access pattern, at some point, they could learn something about the private input. Then the problem becomes how should we access data without revealing access pattern? There are two ideas might be useful to us. The naive solution is when we need to access a data element, we simply touch every element in this dataset. By doing this, there will be no way to tell which element we exactly visited. But the drawback of this idea is obvious. It will be pretty expensive if the dataset is large. And another solution is using some generic techniques like oblivious rhyme or ORAM. And ORAM is a tool that can sell our access pattern, which would work well for our purpose. And it also has pretty good semi-linear complexity, which is way better than the naive solution. This is the performance comparison of these two options. We select floor ORAM to represent ORAM because when we were working on this work, it has the best performance among all ORAM in the environment of secure multi-party computation. As you can see, ORAM is indeed much better when the data size is large. But however, for the smaller dataset, the naive solution works much better. We think this makes sense because the ORAM is not designed for a small dataset. So we decided to look into this problem and see if we could do better for the small to medium dataset. This is the main contributions in our paper, but in this talk, I will only discuss the first two parts. I will first introduce our generic array access protocol, which could work for any number of parties, and then I will introduce our another solution, which could work only for the three-party environment. Before we talk about our work, I'd like to introduce a little bit about the setting we used in this work. We will assume that there are n combinational parties, where T parties are semi-honest. These semi-honest participants are guaranteed to follow the protocol, but might attempt to learn unauthorized information besides the information they have. Also, we assume the majority of the n parties are honest, which means that the number of semi-honest parties, should be less than half of n. And second, in this paper, we mainly use secret sharing technique to protect the private data. So if we use a bracket value, it means that this value is shared among all parties, where each party only holds a share of it. So if someone wants to reveal or open a secret shared value, they have to collect more than T+1 shares. Then let's look at the first protocol. So the first question is that where should we start with? So actually, by using the secret sharing technique, we have two options to do so. The first approach is a multiplexer-based approach. So in this approach, we just bit decompose the private index and use these bits to select the target value that we want. So the second approach is a comparison-based. And in this approach, we just compare the private index with each array index and chooses the one that matches. Actually, the complexity of these two approaches are similar, but in Pico's implementation, we found that the second one is slightly faster. So we decided to look into the second one and see if we could find something redundant. Then let's look into the comparison-based approach. So in this approach, if we say we have a private location denoted as J that we want to read, we first compare this location J with all indices. So of course, only one of these comparison results gonna be true. The rest just gonna be false. Then we can do a dot product between the comparison results and each array element. Then only one element that has the matched index will be selected out. So our first observation is that the comparisons might be redundant because we just compare the index G with 0, 1, 2, and 3, and all these indices are pretty similar and always has the same and known differences. So we decide to look into the equality function here more carefully. Then we noticed that this equality function is implemented using a function equality to 0. So as you can see, the equality function takes two inputs, the private index J and the index I. So if we want to compare J and I is equal or not, we could feed the difference of J and I into this equality to 0 function to check if their difference, or just J minus I, is 0 or not. Then let's look into the equality to 0 function. So the idea of this function is that we first create a long random value and use it as a long mask to protect our argument that we could open it later. The mask should be longer because this is logistic padding. So next, we generate all the bits of the opened C and use these bits to generate the bits of the original argument or the private input. So this is did in the on the line 4 by using XOR. So then we combine all the bits of the original input A using OR operation at the end. So we notice that in this structure, the first step that is used to generate the randomnesses is the most expensive part, which has linear complexity, and also the OR operation at the end is also costly, which has similar linear complexity. So as we said before, we think these equality comparison might be redundant. So actually in this structure, the first redundance we found is the random generation, because the difference we fit into this function, which we say J minus I, is related because on each time I is increasing by 1. So the difference we fitted into this function is decreasing by 1 for each time. So the difference is known. So we think there's no need to protect all of these differences. So instead, we may only need to protect the private index J once, and later on, once we open the protect value with a C, and we could produce J minus 1, J minus 2, J minus 3. We could produce these differences just by doing C minus 1, C minus 2, C minus 3. So after we optimized the randomness generation, the complexity of the entire array access protocol is reduced from order of m log m to order of m log m. But we still think this is suboptimal. So let's go back to the equality to 0 function. So as we said before, the KR function at the end of this protocol is somehow costly. And this function is used to calculate OR of all these log n bits. So we think that in each core of this equal to 0, this KR function will be called. And the values that be fed into this function are pretty related. So instead of generating this all one at a time, we think we could generate them more efficiently. Thus, we proposed our own OR function to do so. So our OR function used a divide and conquer approach. So we first divide the entire size into two halves and recurse on each half and then assemble all the results. So instead of call the k or for m times, right now we only need to call our OR function for only once. So after applying all the optimizations we discussed before, you can see that the performance of our array read protocol has been improved a lot. So right now, our new array read protocol could outperform all the other options when the dataset size is smaller than 2 to 14. Let's look at our second solution. So this protocol is designed for three-party only. Instead of using Shamir secret sharing, in this work, we use 2 out of 2 additive secret sharing. So you could, if you see a value in a double bracket with a subscript P1 or P2, it means this value is secret shared among two parties, and P1 or P2 is the party that holds this share. So in this work and in this protocol, we use rotation to protect or to hide the access pattern. So we will rotate the entire array for 2 times. In the beginning of the protocol, you could see that the entire array is shared among two parties, the party 1 and party 2. In the first rotation, party P1 and 2 will locally rotate their own share by an offset R1, where R1 is a random number that both parties agree on. Once the rotation is done, party 1 will try to reshare its own share to P2 and P3. So party 1 will first generate a bunch of random shares we denote as S. Then party 1 will use its original share to minus the random share to get another half of the shares. Then P1 will send one piece of this share to P3 and send another half of this share to P2. Once party 2 received the shares from P1, it will first combine its own shares with the received shares to get its new shares. You can see that once this is done, the shares held by party 2 and party 3 are still two pieces of the 2 out of 2 additive secret shares of the original array, which has been rotated by a number of R1. Next, let's start to do the second time of rotation. This time, party 2 and party 3 will locally rotate their own share by another random number, R2, where R2 is also agreed by these two parties. Once the rotation is done, party 2 will again reshare its share to the other two parties. Also, party 2 will first generate a bunch of random shares, which we denote as S'. So party 2 will then use its own share to minus the new generated random shares to get another half of the shares. So party 2 will send one piece of share to party 1 and send another piece of share to party 3. Once party 3 received shares from party 2, party 3 will combine its own share with the received share to get the new share. At this time, you could see that the shares held by party 1 and party 3 are still 2 out of 2 additive secret shares of the original data, which has been rotated by 2 times by an offset of R1 plus R2. In the last step, we open the final location of the target element, which should be located at J plus R1 plus R2. Because the private index J is protected by random numbers R1 plus R2, we claim that no party could learn anything about the original private index J. On the one hand, although party 2 knows the value of R1 and R2, but the value of J plus R1 and R2 is not open to it. And on the other hand, party 1 or party 2 only know one random element, so they also have no idea about the private index J. In this figure, the blue plus is for the performance of our custom three-party array read protocol. You could see that our three-party array read protocol outperforms all the other options or solutions when the size of the dataset is smaller than 2216. So in this talk, I will briefly introduce our generic array access protocol as well as our custom array access protocol, which only work for 3 parties. Thank you.